Okay, so for today, what we're going to get into is some more basic electrical circuitry and some Ohm's Law. Now, with Ohm's Law, it's kind of a theory that really just breaks down how your voltage, your amperage, and your resistance in an electrical circuit kind of like work together so that we can use electricity in a useful way. But the definition really for Ohm's Law in general is that it explains the relationship between current, voltage, and resistance. Another term for voltage is electromotive force, or EMF. The formulas that we use for Ohm's Law is relatively basic and pretty much generic. The basic one that we always kind of think about when we think about Ohm's Law is I equals E divided by R. The I stands for amperage, or impedance is another word for it. That's where the I comes from. The E in Ohm's Law stands for electromotive force, or better known as volts. R represents resistance, or ohms. Okay? So when we're doing Ohm's Law, it is really good practice to kind of draw a circle like you see here on the screen and put an E, an I, and an R, as you see. So when you are calculating your formulas, you can easily identify what formula you need to use to calculate what you're trying to find. So for example here, if I took my thumb and I just covered up the E, my formula to figure out what voltage I'm looking for is using the formula E equals I times R. If I was to look for current, which is the I, if I was to cover up the I, that would be now E divided by R. And if I was to try to find resistance, I would cover up the R, and now I would have E divided by I. So here's an example of Ohm's Law. We have a simple circuit here where we have 120 volts, and we're dealing with a 20 ohm resistor, or a 20 ohm load. Okay, so what we want to try to find is what current can this particular type of circuit deal with. So to find that, we would have to use the formula I equals E divided by R. Okay, so all we have to do is plug in our known variables, which is nice about Ohm's Law. As long as you know two variables, you can find out the third. So we would take this guy and we would go I equals 120 volts divided by 20. And we come up with 6 amps. So here is the 120 volts, and we're going to divide it by 20 ohms. And that comes up with 6 amps. So this circuit here would be able to handle at least 6 amps of current. So remember, back to some of our basics, concepts of all of our electrical circuits. Any electrical circuit that we have has to be complete. It has to have a complete path for an electric current to flow. It has to have a power source. It has to have a load. It has to have a switch in there in order for it to be considered a complete circuit. Okay, when the circuit is complete, so that the current can flow, it is termed closed. When you hear that term, is the switch closed? That means, is the switch on, or is the switch in the on position? Is the electricity flowing? When you have a path for current to flow that is interrupted, that means that the circuit is open. When we turn a light switch off and our light turns off in a room, we have opened that circuit. The electricity is now no longer flowing. It has been interrupted. All electrical circuits, they have to have a complete path for electricity to flow. Okay? It has to have a source, again, for where that electricity is going to come from. Some electric devices, loads that require electrical energy for its operation. We got to have something in that circuit that's going to use that electricity to do work, whether that's a motor, whether that's a light, whether that's a solenoid, something in that circuit. If I don't have a load in that circuit, I am going to create a short. That's going to possibly pop a breaker. It's going to blow a fuse. It's going to do something that is going to render that circuit inoperative. So again, a basic concept of a circuit. Again, here's our power source, our generator. Okay, that generator is sending power out to our light bulb. The light bulb is on. Okay, a byproduct of resistance in a light bulb is light and heat. So we are using that electricity to do something. It comes out, it goes into our switch in this case. Our switch is on which would be our neutral side of the switch, which is perfectly fine, because a switch is nothing more than a power passing device. It could be on either side. As long as you're using it to make and break a circuit, you're okay. So here you are, you have an open switch or a closed switch. If I close it, electricity is allowed to pass through that switch and then right back to the power source. Okay, switches in series for series circuits and controls are commonly wired in series with each other to control one or more loads. So that could be relays, it could be contactors, for example. Okay, it could be simple single pole, single throw switches, single pole, double throw switches, whatever is in that circuit, it's going to be wired in series with a load so that we can turn it on and off. Okay, the simplest of all circuits is obviously the series circuit. Okay, series circuits allow for one path of current to flow through a circuit. Okay, a great example of that is the old Christmas lights. When one light went out, they all went out, and you would watch Dad go crazy trying to figure out why the strand of lights wasn't working. Okay, so here's an example of a pictorial and a ladder diagram of a series circuit. So here is our power source, here's our generator, here's our switch, here's our paths, here's our loads. Okay, one right after another. And if one of these loads happen to break or open, the electricity would no longer be able to flow through that circuit, and that entire circuit would not work. Down here is a simple ladder diagram of the very same circuit, just drawn differently, but representing the exact same thing. Here is our generator, our circle with the little squiggly line right here. Here's our generator, here's our switch, here's our paths and our loads. Okay, so characteristics of a series circuit and calculations for current, resistance, and voltage. Well, when we are dealing with a series circuit, okay, current is drawn through that circuit throughout the circuit the same way. Okay, current in a series circuit does not change in a series circuit. It remains the exact same number because it only has one path for that electricity to flow. Okay, total resistance in a circuit, in a series circuit, is simply the sum of all of the resistances added up together. So when you're looking at a series circuit or all the light bulbs in a old strand of lights, all you're doing is taking an ohm reading of each individual light and adding them up. Okay, R1 plus R2 plus R3 plus R4, so on and so forth until you have no more loads in series. Okay, and that will give you your resistance total. Okay, the voltage in a series circuit is completely used by all of the loads in the circuit. However, the voltage that is used by each load is going to be different. The reason why it is different is because of the different resistances of each of those individual loads. Not one of your light bulbs, motors, solenoids, coils, whatever it is that you're dealing with in an electrical circuit is going to be the same resistance. Okay? When we are taking these readings of the voltages across each one of those loads, we consider that a voltage drop. We're reading what that load is actually using. Okay, the voltage drop is the amount of voltage used or lost through any load or conductor in the process of moving the current through that part of a circuit. Okay, the sum of the voltage drop of any part of a series circuit is going to be equal to the voltage being applied to the circuit. So when you're going across each one of your loads, load 1, load 2, load 3, if you take those readings, it should add up to your source voltage. For example, say you have two loads wired in series and they're both using 60 volts of electricity. 60 plus 60 equals 120 volts. You should have that total at the end. Okay, here's another example. This one here, we want to calculate the total resistance, we want to total the voltage drop for each one of our elements, and we want to calculate the current for each one for this entire circuit. So how do we do that? Well, we know that in a series circuit, we need to add up the total resistance of each one of our loads. So we have 5 ohms, 20 ohms, 50 ohms, and 35 ohms. So what we're going to do is we're going to take 5 plus 20 plus 50 plus 35, and we're going to come up with a number. Okay? That number, using our formula, R1 plus R2 plus R3 plus R4, we come up with 110 ohms of resistance. Okay, we are dealing with a 120 volt circuit. Okay, that's another form of information. Remember, as long as you have two known variables, you can figure out the next. So we have 110 ohms of resistance in this one circuit. But now we want to figure out what the amperage is. To figure out the amperage, we now have to go back to our Ohm's Law formulas. I equals E divided by R. So we're going to plug in our numbers that we know. We know that we're dealing with 120 volts. We know that we have 110 ohms of resistance. So the formula we use is E divided by R, which is 120 volts divided by 110 volts. We come up with 1.09 amps. That is what that circuit will most likely be able to handle. Okay, to find the voltage drop for each one of our elements in this circuit, now remember the voltage drop across each element in the circuit can be determined by rewriting Ohm's Law. E equals I times R. Okay, so for our 5 ohm resistor, we're going to take our known amperage that we now have of 1.09 amps, and we're going to times it by 5, by that first resistor. That guy is going to use 5.45 volts of electricity. The 20 ohm resistor, we're going to use the exact same formula, 1.09 amps times 20 ohms of resistance, and that guy is going to be using somewhere around 21.8 amps, or 21.8 volts, sorry. The 50 ohm resistor, 1.09 amps times 50 ohms, that guy is going to use 54.5 volts of electricity. And then the 50 ohm resistor, you're going to have 38.15 volts of electricity. Okay. Now, if you add all of those voltages up, 38.15, the 54.5, the 21.8, and the 5.45, you should come up with what we started with, the 120 volts of electricity. Okay. In a parallel circuit, it's a little bit different. Okay. Remember, in a parallel circuit, we have more than one path for electricity to flow. Okay, your electrical devices are arranged in the circuit so that each is connected to its own supply voltage. Now think about the newer Christmas lights that are out. You know, if one light bulb goes out, the rest of them will still remain on. Well, that's a parallel circuit. Okay, parallel circuits are the most common in the HVAC industry and in the electrical industry. So we are going to be seeing and dealing with a lot of different devices that operate off of line voltage. Okay, line voltage is the electricity that's being supplied to that equipment. Okay, that could be 120 volts, it could be 240 volts, it could be 480 volts, whatever that voltage is going to be. Okay. An example of parallel circuits is standard wiring in pretty much every single residence out there. Okay, every light switch that you have in a home is wired in parallel so that it can control a device in your home. A light, it's going to use to control an outlet, it's going to use to control your television, and so on and so forth. Okay, so here's the example of a parallel circuit. Again, here's our power source, which is our generator, okay, our switch. Here's our paths. Here's one load, two loads, and three loads. If one of this bulb happened to go out or this resistor happened to break, this circuit would not work, but the rest of them would still work. Okay, the current draw in a parallel circuit is determined for each part of the circuit depending on the resistance of that portion of the circuit. So the total current draw of the entire parallel circuit is the sum of the current in the individual sections of your parallel circuit. Okay, the resistance of a parallel circuit is going to get smaller as more resistances are added to it. The total resistance in a parallel circuit cannot be obtained by just taking the sum of all the resistances. We have to use a specific formula based off of the amount of loads that we have in that circuit. So, for example, if we have a parallel circuit with only two loads or two resistors, so to speak, in that circuit, we have to use the formula R1 times R2 divided by R1 plus R2. Okay, if the resistor has three or more loads in parallel, you are going to use the formula 1 divided by R1 plus 1 divided by R2 plus 1 divided by R3, and so on and so forth, which equals 1 divided by R resistance total. Okay, the voltage drop in a parallel circuit is the line voltage being supplied to that load. So here we are, we have an example of a parallel circuit that has two resistors or two loads wired in parallel. Okay, so we're going to have to use the formula of the R1 times R2 divided by R1 plus R2 to find our resistance. So we know that we have a 15.5 ohm resistor and a 35.7 ohm resistor, and we're dealing with 120 volts of electricity. So for this one, let's figure out the current draw for each of our individual loads. When we are doing that, we have to break that circuit down into individual sections. So we're going to focus on the 35.7 ohm resistor. So we're going to be focusing on this guy right here. To figure out what the amperage draw of that branch or this parallel circuit would be is we take the 120 volts and we divide it by 35.7 ohms. That's going to give us 3.36 amps. That branch of that parallel circuit will be able to handle that much for amperage. The 15.5 ohm load or resistor, we do the exact same formula, 120 volts divided by 15.5 ohms, and we come up with 7.74 amps for that particular circuit. If we want to determine the total resistance for that parallel circuit, now remember we have two loads that are in parallel, we are going to take 15.5 times it by 35.7 divided by 15.5 plus 35.7. So once we plug in those numbers, 15.5 times 35.7, we come up with 553.35. And if we add those two together, 15.5 plus 35.7, we come up with 51.2. So we take 553.35 divided by 51.2, and we come up with 10.80 ohms of resistance. So to determine the current draw of that circuit, we now have to take that number that we just calculated, the 10.80, and plug it into our Ohm's Law formula of I equals E divided by R. So that's 120 volts divided by 10.80. We come up with 11.11 amps for the total current draw of that circuit. Now, with more complex type circuits, it kind of gets a little bit more complicated when it comes to trying to calculate your values. But those complicated circuits are better known as what we call a series and parallel circuit. But what we can honestly do with that is we can take circuits like this and break them down into simpler circuits to figure out what types of values that we're looking for. The easiest way to do that is start with small, simpler chunks of the circuit that you know how to work with, that's either all series or all parallel. And then as you do that, you're going to then redraw that circuit for each step as it simplifies. So for example, here we have a series and we have a parallel circuit, right? What we would want to do with this type of circuit is we know that we're going to want to calculate the resistance for this series circuit. So we know that that's R1 plus R2. We're going to take that guy and we're going to add those two together. And we're going to come up with basically just one resistor. After that, we're going to want to focus on that parallel circuit. Remember, we have two loads in parallel. So you're going to use that R1 times R2 divided by R1 plus R2. And you're going to get a number for that circuit. Once you get that number, you can basically draw that circuit as if it's just a series circuit, and then you just add the two resistances together, and then just simply plug in your formula through your Ohm's Law, and you can pretty much calculate what that amperage, resistance, and voltage of that particular circuit can actually handle.